Hello and welcome to lecture 24 of analog integrated circuit design. In this lecture we will deal with one of the very important non-ideal features of any real circuit, that is random noise. It turns out that dissipative components like a resistor or a MOSFET have random noise, and components which do not have any power loss like capacitors and inductors do not. So, we in this lecture we will look at the random noise in a resistor. As Ohm's law says, if you pass a current I through a resistor R, the voltage across that should be I times R, and if you apply a voltage source V across a resistance R, the current through that will of course be V divided by R. Now, in reality, because of random motion of carriers through the resistor, the current is not exactly V by R. Okay. Let us say you take this circuit and measure the value of I very precisely versus time. You will see that the current has a mean value of V by R, but there are variations around this mean value, and that happens because if you take any cross section of a resistor, let us say a current I is flowing that way, I equals V by R. That means that on average this much charge is flowing every second through the resistor, but if you do take a cross section and see the charge flowing across the cross section, in addition to this average value there will be charges randomly moving back and forth across the cross section. This is because of random thermal motion of charges. Okay. As long as the temperature is above absolute 0, this is going to happen. Now, we need a way to quantify this and also to estimate it in any given circuit. Okay. Clearly, because of this, the current in any circuit is not exactly what we calculate based on the device relationships. Okay. So, how can we specify something that is random such as this? First of all, the resistor noise. It turns out that if you do this experiment with two different resistors, the noise waveform that you see here will not be the same, they will be uncorrelated. From one resistor to another. Okay. It is a random phenomenon, and what is happening in one resistor does not have anything to do with what happens in another resistor. It turns out that in the particular case of a resistor, it is uncorrelated from one time instant to another. Okay. So, if you take the value at a particular time and another time in the same resistor, they will also be uncorrelated from each other. Okay. How can we quantify such a random quantity? There are many ways. From your study of probability and random processes, you will know that you can specify the power spectral density, or in general the spectral density, which relates to how the randomness, the energy in the randomness is distributed over frequency. Okay. You can also specify the mean squared or the root mean squared value, one of these things, and for 0 mean random processes, these are the same as the variance and the standard deviation. Okay. Now, in this case we assume that the average current is V by R and the rest of it is noise, and by definition it will have 0 mean. Okay. So, we can either call it the root mean squared value or standard deviation or either mean squared value or variance. Okay. We have to specify one of these things to specify the size of the noise, because noise is random we can't specify the amplitude. In fact, theoretically the amplitude of such a noise it turns out to be infinity, but we can specify the size of the noise by specifying the mean squared value of the noise. Okay. We need to learn how to do this for a resistor. First of all, let me go back to the two pictures I drew earlier. If I have a voltage source across a resistance, the current I equals V by R plus some noise current, okay. And this can be modeled by assuming that there is a noiseless resistor and a noise current source across it. Okay. The arrow is just to symbolize that it is a current source, that does not mean that the current is always in this direction. As I said, the mean value of IN is 0 and the current can flow in both directions. Clearly, in this case also I will be equal to V by R due to the noiseless resistor plus IN. Okay. So, we model the noise in the resistor as a current source. Okay. If I look at the alternative description, if I pass a current I through a resistance R, the voltage across it will be I times R plus a noise voltage, and this again can be thought of as the current flowing through a noiseless resistor and a series voltage source which is equal to the noise voltage. Okay. In this case also the voltage across it is I times R plus Vn. So, in the pictures on the right side, what is done is the noise itself is abstracted out as a source, and this is a very common thing. You assume that there is a noiseless component which follows the VI relationships that you know. It is Ohm's law for a resistor or square law for a MOSFET and so on, and the noisy part of it is modeled out as either a voltage source or a current source, whichever is convenient. Okay. Now, finally, if we are going to use this model or that model for a resistor, the two have to describe the same thing, okay. And that will happen if IN times R equals Vn. Okay. This we can see very easily by assuming that, let us say we have applied a 0 voltage source across the resistor. And by the way, this is noiseless. So, the current flowing here is IN. Okay. This entire thing, the combination is what models the resistor. Now, I should get the same result if I use the other model for the resistor noise, which is a resistor, noiseless resistor in series with a voltage source Vn. Okay. And I short circuit it just like here. Clearly, the current here will be Vn divided by R, okay, and the currents here and here have to be the same. So, that means that the equivalent voltage source of a resistor and equivalent current source of a resistor are related by a ratio which is equal to the resistance R. Okay. As I mentioned before, we cannot specify the instantaneous value of either IN or Vn. Okay. So, what we will specify instead is the spectral density, that is how the energy in Vn or IN is distributed over frequencies. Okay. And IN and Vn are noise in a resistor R. Okay. Now, first of all, what is the spectral density? Spectral density is some function of frequency, and as is common in circuit design, we take the one sided spectral density. That means that we specify the spectral density for positive frequencies. And what the spectral density tells you is some function, the spectral density of IN will be some SI of f, okay. And what is this? This is related to the autocorrelation function of this process IN through the Fourier transform. It is the Fourier transform of the autocorrelation function, and in particular the integral of SI over all frequencies 0 to infinity will be equal to the autocorrelation function at a time shift of 0 or the variance, okay, sigma squared. So, this is how the spectral density is useful in specifying the magnitude of the noise. Okay. Now, for a description of autocorrelation function, spectral density and so on, you can refer to any basic book on random processes. It turns out that in the particular case of a resistor, if I plot the spectral density of the current, it is constant for all frequencies. Okay, and such a function is known as white noise. Okay. If the spectral density of a certain noise process is constant for all frequencies, it is known as white noise, analogous to white color which has all frequencies in it. Okay. And the magnitude of the spectral density is 4 kT divided by R, where K is Boltzmann's constant, (1.38) times 10 to the minus 23 joule per Kelvin. Okay. And T is the absolute temperature, and room temperature corresponds to 300 kelvins. Okay. Now, this is the spectral density of the noise current of a resistor. It is constant over frequencies and it has a magnitude equal to 4 kT divided by R. Okay. Now, we also know that the noise voltage is related to the noise current by a multiplicative factor R. So, the noise spectral density of the voltage is related to the noise spectral density of the current by the square of the multiplying factor. Okay. This is because basically the spectral density relates to the square of these quantities. Okay. So, that means that the noise voltage of a resistor has a spectral density which is 4 kT divided by R times R square equals 4 kT R. Okay. Naturally, that is also constant with frequency and it is 4 kT R. Good numbers to remember are that kT equals 4 times 10 to the minus 21 joules at 300 Kelvin. Okay. And if you calculate, let us say for R equals 1 kilo ohms, what we will get is 4 times 10 to the minus 21 joules times 10 to the 3 ohms, and this gives to 16 times 10 to the minus 18 volt square per hertz. Okay. The voltage noise is specified in volt square per hertz. It is related to the square of the voltages, and the spectral density obviously relates to a density over frequency. So, it is given in volt square divided by hertz or volt square per hertz. Okay. Similarly, the current noise spectral density is given by units of ampere square per hertz. Okay. And as I mentioned, for a 1 kilo ohm resistor, SV turns out to be 16 times 10 to the minus 18 volt square per hertz, and clearly from that we can also calculate SI, which is 16 times 10 to the minus 24 ampere square per hertz. Okay. Now, we did not derive any of these results, we just took them for granted. These results were derived by Nyquist long ago, and they have been used very widely and then confirmed experimentally and so on. Okay. But what does it mean? I mean, we have these abstract descriptions of noise in terms of the spectral density and so on, and we said something about it being related to distribution of these quantities over frequencies. But when we deal with circuits, we deal with voltages and currents, right. I have a 1 volt signal here and I have a 10 millivolt signal there and so on. Now, noise is something that is random, and I should like to specify it also in terms of voltages or currents. Okay. Then I can compare my signal to the noise and see if the signal is sufficiently above noise. Now, from common experience, you know that if you are trying to decode some signal, or let us say you are trying to listen to something and there is a lot of noise, you will not be able to. If there is very little noise, you can. Okay. So, you have to be able to quantify the amount of signal to the amount of noise, and for that we need to be able to describe the signal and noise in the same units, and we describe the signals in terms of voltages or currents. Similarly, we have to do the same for the noise as well. Okay. So, what is the meaning of the spectral density then? What it means is that, let us take the voltage noise spectral density of a resistor, okay, and a resistor is modeled by a noiseless resistor in series with a noise voltage source. So, across this there will be some voltage, although you expect there to be no voltage because no current is flowing, because of noise there will be some voltage. And let us say you apply this to an ideal band pass filter of some bandwidth B, okay, and at the output there will be some other voltage, let me call it VO. Okay. Now, how to use the spectral density is that the spectral density has a certain value 4 kTr, in this case it happens to be constant with frequency, and let us say we have a band pass filter B at a center frequency of f naught. So, that means that at f naught I have an ideal band pass filter whose bandwidth is B hertz. Okay. So, that means that in this range of frequencies it will pass the input voltage as it is to the output, and outside it does not. Okay. So, then it passes the noise energy in the pass band of the filter and blocks all of it in the stop band of the filter. Okay. Then the spectral density times the bandwidth, okay, because inside the band the transmission is constant, it simply passes the noise. This will be equal to the variance of V naught. Okay. So, that is what it means. So, for instance, let us again take a 1 kilo ohm resistor. It has a noise spectral density, voltage noise spectral density of 16 times 10 to the minus 18 volt square per hertz, and if I pass it through a band pass filter, ideal band pass filter of 1 megahertz bandwidth, okay, this means that B is 10 to the 6 hertz. Okay. So, the spectral density times B will be 16 times 10 to the minus 12 volt square, and this is the variance of the output voltage. Now, we would like to specify the RMS value, and that is nothing but the standard deviation, and sigma VO will be square root of SV times B, which will be equal to 4 times 10 to the minus 6 volts or 4 microvolts. Okay. So, this is how the voltage noise spectral density or current noise spectral density can be used for calculating the amount of noise. Okay. When we say the amount of noise, we have to be able to quantify it, and here we have said that the standard deviation of noise or the root mean square value of the noise is 4 microvolts. Okay. Now, it turns out that like many other random phenomena commonly seen in nature, distribution of this noise is also a Gaussian. Okay. So, what we would see is, so let us say we have a current I flowing through a resistor R, it will have a mean value of I R, and if I plot the density function, the probability density function versus the voltage, it will have a mean value of I R and it will have some distribution around it. Okay. Now, what does it mean by having a distribution? Let us say you make thousands of these example circuits where you are passing a current I through a resistor R and you measure the voltage across all of them at the same time. Okay. Then you will find that all of them will not be equal to I times R, they will have a mean value of I R, but they will have a distribution around it, and the standard deviation of that distribution will be 4 microvolts. Okay. Now, it also turns out that you take one of these circuits, you pass a current I through a resistor R and you measure the noise at different time instants. Let us say you do it at some 10,000 time instants, then they will also have an average value of I times R, but they will have a distribution around I times R, and the standard deviation of that distribution will also be 4 microvolts. Okay. So, that is what it means. You cannot specify the noise at any instant of time, but you can specify the root mean square value and draw whatever conclusions from that. Now, given that the distribution is Gaussian, we can say that 99% of the time the values will lie within plus minus 3 sigma of the mean. Okay. So, this is something that we know from the knowledge of the Gaussian distribution. Okay. So, we can expect that most of the time the voltage that you measure across this resistor will be within plus minus 12 microvolts of the mean value I times R. Whether this is sufficiently close or not, that depends on the application. We will later see examples of how to calculate that, but we will know that if you pass a current I through a resistor R where the resistance is 1 kilo ohm and the bandwidth of interest is 1 megahertz, you will have a standard deviation of 4 microvolts, or 99.9% of the time you will measure a voltage within plus minus 12 microvolts of I times R. Okay. Now, because we deal with voltages and currents, sometimes the spectral density, like I said, is 4 kTr volt square per hertz, and this is equivalently specified as square root of 4 kTr volts per square root hertz. Okay. The reason to do this is we prefer to have a units of voltage than volt square, that is all. Okay. And we have the square root of the bandwidth under it. So, what does it mean? Again, for a 1 kilo ohm resistor, we have 16 times 10 to the minus 18 volt square per hertz, and this can be equivalently represented as the square root of this value, okay, which is 4 times 10 to the minus 9 volts per square root hertz, which is the same as 4 nanovolts per square root hertz. Okay. Now, this kind of specification is given so that you can quickly relate it to the voltages. Now, again, when you are talking about 1 megahertz bandwidth, an ideal band pass filter of 1 megahertz through which this noise is passed, all you have to do is multiply the spectral density in volts per square root hertz times the square root of the bandwidth. Okay. Square root of 10 to the 6 is 10 to the 3. So, we will get 4 microvolts right away. Sometimes it is easier to specify it in terms of volts instead of volt square. Similarly, the current noise spectral density, which is 4 kT by R ampere square per hertz, can be equivalently represented as square root of 4 kT by R ampere per square root hertz. Okay. Again, for a 1 kilo ohm resistor, this will turn out to be 4 times 10 to the minus 12 ampere per root hertz, or 4 picoamp per square root hertz. Okay. Because we are so used to dealing with voltages and currents and not squares of voltages and squares of currents, we tend to specify it in volts per square root hertz or in amperes per square root hertz. but the other description is equally valid and also used equally often. Okay. Now, just to give you a little more feel for this resistor noise, let us say I take a 1 kilo ohm resistor and connect it to an oscilloscope. What will I see? According to Ohm's law, there is no voltage across this because there is no current flowing through it, but we do know that the random fluctuation of carriers inside this will cause some voltage. Okay. Now, how much will that voltage be? As usual, we cannot specify the exact value at a given instant, but we can specify sort of the size. So, what will we actually see on the oscilloscope? The oscilloscope itself will have some bandwidth, let me call it BWOSC, and the resistor has a voltage noise spectral density 4 kT R. We will assume that as usual that the voltage across the resistor is sensed without disturbing it by the oscilloscope. So, the variance is that much and the root mean square value is that much. Okay. I will use that sometimes to denote the root mean square value of the signal, and this denotes the mean square value of the signal, and that is 4 kT R times the bandwidth of the oscilloscope. Okay. So, given that this is 1 kilo ohm, 4 kT R is 16 times 10 to the minus 18 volt square per hertz. Okay. And let us say we have an oscilloscope which has 100 megahertz bandwidth. So, this times 10 to the 8 hertz equals 16 times 10 to the minus 10 volt square, that is the mean square value. Okay. And if you take the square root of this, we get 40 microvolts. Okay. It is quite a small value to be measured with an oscilloscope, but let us say you do have an oscilloscope with such a fine resolution. Okay. So, what you will see is you will see a band, right, of some thickness, and because this is a Gaussian distribution, the amplitude is actually infinite. It can take values of plus infinity or minus infinity, but 99.9% of the time it will be within a plus minus 3 sigma band. Okay. And that I will draw as a band, and that is what you will see on an oscilloscope which is displaying noise, and that turns out to be within a band of plus minus 120 microvolts. Okay. So, if you have a sufficiently sensitive oscilloscope and you connect it up to a resistor, this is what you will see. Alternatively, if you want to see a larger noise, you know that the voltage noise spectral density is directly proportional to the resistance value. So, what you can do is to use a larger and larger resistor, so that you will see larger noise on the oscilloscope. Okay. What we did so far was to define the spectral density, that is the distribution of noise over frequency, and if you take a certain band of it, let us say you select it using an ideal band pass filter which passes certain frequencies and completely blocks others, what you will see is the spectral density times that bandwidth, okay, because spectral density is a constant. Now, when the noise voltage of a resistor passes through some circuit, it may not experience a transfer function which is constant over all frequencies. Okay. So, in general, let us say we have some transfer function which varies with frequency, and to its input we connect a noise source, some noise source whose spectral density is let us say SV, and I will call it SVI just to denote the input. What will we see at the output? Again, this is known from basic random process theory, that at the output we will see another noise process, okay, whose spectral density is the input spectral density times the magnitude squared of the transfer function h. Okay. Now, if you want to calculate the output variance, you have to integrate the output spectral density from 0 to infinity. Okay. We will quickly see an example of this one. So, from the input spectral density you can calculate the output spectral density. Now, let us say you have some H of f, and to its input you connect a resistor. Okay. We know that now the noise spectral density of this noise, the noise source here equals 4 kT times R. Okay. The output noise spectral density will be 4 kT R times mod H of f square. Okay. And the mean square value of the output will be 4 kT R integral mod H of f square df from 0 to infinity. Okay. Now, just like any other voltage or current in a circuit, the noise voltage or noise current of a resistor experiences some transfer function when it goes to the output. Okay. Now, when a noise goes through some transfer function, the output is also some noise, and the spectral density of that noise equals the spectral density of the input noise times the magnitude square root of the transfer function. Now, if you have multiple noise sources in a circuit, what you have to do is you calculate the transfer function from every noise source to the output. Okay. Now, this is a very common scenario that you have a circuit with a number of resistors. Okay. Let me call it V1, V2, and sometimes you may choose to model the noise with a current source instead of a voltage source, and let us say the input is 0. Okay. As usual, because of the noise, the output will not be 0. In a linear time invariant network, if the input is 0, the output will be 0, but because of noise sources it will not be 0. Okay. So, how do you calculate the output? We calculate the transfer function from each source to the output. So, let us say VO is V1 times H1, okay, which is a function of frequency, plus V2 times H2 of f plus I3 times H3 of f. H3 has dimensions of impedance, but it does not matter, and so on. You could have all these things. Now, the spectral density of the output will be the spectral density of V1 times the magnitude square of H1 plus spectral density of V2 times magnitude square of H2 and spectral density of I3 magnitude square root of H3 and so on. Okay. Now, the first one comes from just superposition. Okay. We activate each noise source at a time, find the transfer functions and add them up. Now, the noise is expected to be a very small quantity. So, any calculation that you do with noise will be linear. Okay. Now, even if you have a nonlinear circuit, you are familiar with the concept of small signal linearity. Around the operating point, if you have small disturbances, they can be represented by an equivalent linear circuit. Now, the noise will be small and it can be handled by the small signal linear equivalent circuit. Okay. So, the superposition always applies. Now, to go from the first one to the second one, to calculate the spectral density, we made some assumption that this Vn1 and Vn2 and In3 are uncorrelated from each other. That is why we can add up the spectral densities of individual contributions. Okay. If they are correlated, you have to take the spectral density of the whole thing, and if they are uncorrelated, it turns out that the output spectral density will be simply the sum of individual spectral densities. Okay. And this is a correct assumption, because it turns out that if you have physically different components, the noise from those things will be uncorrelated, right. If you have physically two different resistors, the noise from each resistor will be uncorrelated from each other. Okay. The noise from the two resistors will be uncorrelated from each other. In fact, we can simply do a quick calculation to verify that that is indeed the case. So, let me use the current source model. Okay. If I have a resistance R1, it will have a current source whose spectral density is 4 kT divided by R1. This is not the value of the current, this is the value of the spectral density. If I have a resistor R2, I will have 4 kT divided by R2. Okay. Let me call this IN1 and IN2. Now, if I have these two in parallel, what do I get? I get the parallel combination of the resistors, which is the reciprocal of 1 over R 1 plus 1 over R 2, and I will have I n 1 plus I n 2. Okay. And because these two are uncorrelated, the spectral density will be simply the sum of the two spectral densities. Okay. The current sources add up in parallel. So, we will have 4 k T 1 over R 1 plus 1 over R 2. Okay. And you can see that this is consistent, right, because the effective resistance here is such that it is 1 over R 1 plus 1 over R 2. The parallel combination of these two is a single resistor equal to R effective, and you expect that there will be a current source corresponding to its noise, which will be 4 k T divided by R effective. Okay. Now, if we assume that the noise from this and that are uncorrelated, we do get the consistent result. Okay. This is a quick verification. It is very well known that the noise from different components will be uncorrelated from each other. Okay. Now, what we will do next is to take a simple circuit which has a transfer function that is not uniform with frequency. Okay. So far we dealt with an ideal band pass filter which had a uniform transfer function, that is it was either 1 in the pass band or 0 in the stop band. Now, we will look at another circuit, and the circuit is also important for other reasons because its basic results are used in a lot of other contexts. Okay. The circuit we will look at is a first order RC low pass filter and if we apply an input Vi, we get an output Vo, and we know that the transfer function of this circuit in terms of S will be 1 by 1 plus SCR. Okay. Now, this is the transfer function from this input to that output. Now, in this circuit, as usual there will be noise because of the resistor, the capacitor does not add any noise. What we would like to do is to find out the output noise. Now, as I mentioned earlier, noise is calculated from the small signal linear equivalent circuit, and we can do that without the signal, right, because a linear circuit follows superposition, and if we want to find out the effect of noise and signal together, what I will do is I will calculate the effect of the signal separately and noise separately and add up the two. Now, of course, there are circuits in which this is not valid. Okay. Behavior of noise is influenced by the presence of large signals, but most of the common amplifier circuits operate in this linear mode, and whether you have a signal or not, the noise will behave in the same way. So, we will set the signal to 0 and calculate the noise. So, I set the signal to 0 and I represent the noise by the equivalent source Vn. Okay. And I want to calculate Vo. Now, you see very easily that this Vn is in the place of this input. Okay. So, quite obviously the transfer function from Vn to the output is the same as from Vi to the output. Okay. So, V naught of S by Vn of S is 1 by 1 plus SCR. Now, when you are doing calculations with noise, usually we represent everything as a function of the frequency f and not omega, that is f in hertz and not in radians per second. So, we will calculate this as a function of f, and that will be 1 by 1 plus j 2 pi f Cr. Okay. So, from our earlier discussion, we know that SV naught is SVN times the magnitude of h of f square, which is 4 kTr, the spectral density of resistor's noise, times the magnitude squared of 1 by 1 plus j 2 pi f Cr. Okay. Very easy to calculate this, it is 1 over 4 pi square f square c square r square. Okay. Now, what is the shape that this will have? At low frequencies, it has a magnitude of 4 kTr, okay, and at very high frequencies, because of this f in the denominator, it will drop down to 0. And we also see that at the bandwidth of this filter, when f is 1 over 2 pi Cr, this denominator is 2, and we will have a spectral density of 2 kTr, okay, and this is at a frequency of 1 over 2 pi Cr, and after that it drops down to 0 like that, and this is SVO, okay, and this is very much the expected behavior when this is after all a low pass filter. The noise voltage is low pass filtered when it appears at the output. At low frequencies, what happens is you simply have only a resistor, and all of the noise of the resistor appears at the output, and at very high frequencies the capacitor acts as a short circuit and no voltage appears across it, and that is simply what is described by the spectral density plot I drew just now, okay. I would also like to calculate the mean square value or the variance of the output noise, okay. I know that this is SVO integrated over all frequencies, and this is a very simple integral from 0 to infinity. And this there are so many ways of doing it. This gives you a tan inverse function, so that is what the result turns out to be, and that is nothing but 4 kTr 1 over 2 pi Cr times pi by 2, and it turns out to be kT by C, okay. So, the mean square value of the output noise is kT by C in this particular circuit, okay. Now, what does it mean? First of all, when you have a signal also, the output signal will be dependent on the filter's transfer function. So, let us say you have a sinusoid at the bandwidth of the filter, the output will have a sinusoid which has an amplitude reduced by a factor of square root of 2 and phase shifted by 45 degrees. In addition to that, you will have this random noise which is not white because the spectral density is not constant with frequency, but which will have a variance of kT by C, okay. So, the first thing is this is an example circuit for calculating the noise, and if you have more complicated circuits, this is what you do. You calculate the transfer function from the resistor's noise to the output, and if you have many resistor, from each resistor's noise to the output, and add them all up, okay. Now, there is another interesting thing about this, that the noise is independent of R, okay. So, the noise happens to be just kT by C, and in fact, after you become a little familiar with circuit design and interact with circuit designers, you keep hearing about kT by C noise and so on, okay. Now, first of all, why does it come out to be independent of R? This is because if you increase the value of R in this circuit, the spectral density of the noise in the resistor will increase, it is 4 kTr, okay. The voltage noise spectral density will increase, but the bandwidth which is 1 over 2 pi Cr will decrease in the same proportion, okay. Now, the integrated noise is nothing but the spectral density times the bandwidth. Of course, this filter is not an abrupt brick wall filter which allows everything within the bandwidth and stops everything outside the bandwidth, okay. But still the principle is the same. You have spectral density which is increasing in proportion to the resistance and a bandwidth which is decreasing in direct proportion to the resistance. So, the product happens to be a constant, and that is equal to kT by C, okay. So, let us take some values. Let me take C to be 10 picofarads, okay, and let me take R to be, let us say 100 kilo ohms, okay. So, 1 over 2 pi C R equals 1 over 2 pi 10 to the minus 11 10 to the 5 equals 10 to the 6 pi 2 pi hertz, okay, or 159 kilohertz or so. And for this 100 kilo ohm, the noise spectral density 4 KTR will be 16 times 10 to the minus 16 volt square per hertz, okay. So, let us say it is somewhere here and then it drops down to 8 and then drops off like that, okay. Now, let us say I make my R equals 200 kilo ohms. What happens is the bandwidth drops to 10 to the 6 by 4 pi hertz, okay. So, it goes here and the spectral density increases at low frequencies, but then it drops off more quickly when it does that, okay. And what is the variance after all? It is the area under the spectral density curve from 0 to infinity, okay. So, the spectral density here is 32 times 10 to the minus 16 and this is of course in volt square per hertz. It just turns out that the area under this red curve is exactly the same as the area under this black curve, okay. So, regardless of the value of the resistor in a low pass filter, you will have an integrated noise of kT by C. Now, this also tells you, which we will see in examples later, that if you have a circuits with resistors and capacitors and so on, to lower the noise you will end up having to increase the value of the capacitors, okay, which typically increases the area and we will later see also increase the power dissipation, okay. So, that is what we learn from this particular analysis. Now, also this analysis throws up other interesting questions like I have a resistor across a capacitor, okay. This is simply the same circuit redrawn. What I have calculated is the noise of this circuit, right. And as we see, the variance of the capacitor voltage is kT by C independent of the value of the resistor. So, the question is what happens when R goes to infinity, okay. So, we have only a capacitor, but we seem to say that the noise across that is kT by C independent of resistor. So, mathematically the result is valid even when R goes to infinity, okay. So, it is an interesting problem, you can think about it, you can think about what interpretation it leads to, okay. What it means to have R equal to infinity in this circuit and still have a variance of kT by C for the capacitor voltage, okay. Now, there is another way of arriving at this result which I will not deal with in detail. From the equipartition theorem, which you may remember from statistical mechanics, each degree of freedom has an energy of kT by 2. Now, if you have a circuit with one capacitor like this, okay, there is 1 degree of freedom, the capacitor voltage, and the energy of that is nothing but half C V C square, and that will be equal to kT by 2, okay. And from this you see that the mean square value of the capacitor voltage is kT by C, okay. Now, the result of this equipartition theorem is a fundamental result in thermodynamics, and that is how in fact the noise spectral density of the resistor is derived in Nyquist's original paper. But this is rather abstract and it is very hard to make circuit calculations from this very easily, okay. So, we will use the spectral density of the resistor and from that calculate the transfer functions and from that calculate the variance. But this is something of interest that you should know and you can follow the literature for more details on this one, okay. And finally, the noise spectral density of a resistor is 4 kTr for all frequencies. Okay. Now, what does this mean? The variance of this will be infinite because the bandwidth is infinite, right. 4 kTr integrated from 0 to infinity will be infinite. So, if I take a resistor and measure the voltage across it, will I measure infinity? What do you think? When clearly not, because if you do have infinite voltage across the resistor, none of the small signal assumptions would be true and no circuit that you make will ever work. So, many things happen. First of all, your measuring instrument will have some finite bandwidth. So, that will limit the amount of voltage that it measures. Okay. So, that is one thing, and a resistor itself will have some parasitic capacitance across it, because between any two terminals there will be some capacitance, and across every resistor there will be some capacitance, however small. If you make the resistor physically smaller, the capacitance will be smaller and so on. Okay. So, that is another thing that limits the noise, but even more fundamentally, the noise itself turns out to be not white. Okay. This again I will not elaborate on, but from your first year physics courses you may remember what is known as the ultraviolet catastrophe that led to the introduction of quantization and quantum mechanics. Okay. So, initially it was assumed that the distribution of energy across frequencies was uniform, and then it led to this prediction that a black body will radiate infinite power, and that was resolved by Max Planck, who postulated that the energy is only in discrete packets and that proportional to the frequency of the signal, proportional to the frequency of the radiation, and that gives you a result that makes sense, that it has a finite energy. Okay. And the result of all that is that basically this kT will be replaced by h nu divided by exponential of h nu by kT minus 1. Okay. So, this kT is something independent of frequency, but this function is very much dependent on the frequency, and h is Planck's constant and nu is the frequency, and you can very easily also see that when the frequencies are very small, h nu is much smaller than kT, this reduces to kT. Okay. So, essentially what we have is a low frequency approximation to the reality. H nu by exponential h nu by kT minus 1 approximates kT for very low frequencies, and that low frequencies includes frequencies up to terahertz and so on. So, we can safely use this white assumption for all our circuits. Okay. Thank you. In the next lecture we will deal with the noise in other components like the MOSFET.